function derivation. So let us consider the Bose-Einstein statistics. It is simply called as B.E. statistics. So this Bose-Einstein statistics is applicable to the system consisting of indistinguishable or identical particles. Okay, indistinguishable means there is no difference between the one particle to another particle. They are exactly same. And those particles are identical. For example, if you take the system of electrons, all the electrons are observed to be same. There is no difference between them. First electron is identical to second. You cannot differentiate the first electron with the second, second with the third, etc. Okay. Then according to Bose-Einstein statistics, for a given macro state, that is for a given energy state, there are different possible microstates. Okay. So there are different possible microstates, and that is called as degeneracy. Okay. So what it says, for a given macro state, you can find number of microstates for a given macro state. Okay. So for a given macro state, there are number of microstates, and this is called as the degeneracy. Okay. Degeneracy. So if you study quantum mechanics, there you can study this concept of degeneracy in detail. But you remember, so for a given energy state, if there are different possible microstate, that is called as degeneracy. Okay. So degeneracy. Then next point is, there is no restriction on a number of particles to occupy a given state. In a given state, you can find any number of particles. Okay, there is no restriction on of particle for a given state. In first state, there may be 1000 particles, 2000 particles, whatever may be the number of particles present. So according to this Bose-Einstein statistic, these are the major conditions. Based on these conditions, we can derive the expression for Bose-Einstein distribution function. So let us consider an isolated system consisting of n identical particles. Let us take the isolated system consisting of n number of identical particles. Then according to the conservation law, the number of particles in a system is going to be constant. So number of particles in the system is conserved. So that conservation of number of particles gives you the summation of ni equal to n. So where ni is number of particles in the ith state, where I runs from 1 to n, and change in the number of particles is going to be 0. That is what the conservation law says. So it says that the total number of particles in a system is always conserved, so that you will get the expression summation of dni is equal to 0. Already you have discussed that. Similarly, we have the conservation of energy in the system. The total energy is given by this expression, that is summation of EINI, that is equal to total energy E. Since energy is conserved, the energy should be constant. There should not be any change in energy. That's why the value of dE, change in energy dE, should be equal to 0. And that dE is given by summation of EI dNi, that should be equal to 0. So these are the conservation equations in statistical mechanics. Already you have studied that the number of particles in the system are conserved, the total energy of the system is also conserved. And mathematically, you can represent these conservation laws by using these two expressions. That is summation of dni equal to 0 and summation of ei dni equal to 0. Okay. Then in B statistics, all states have equal probability in accordance with the equal a priori postulate of probability. Okay, there is a postulate called equal a priori probability. So all states, all microstates are having equal probability. Okay, they are equally probable. So let us take the system where Gi is the number of microstates corresponding to the energy Ei. The energy Ei has a number of microstates, and that number of microstates is Gi. That means one can find different states with the same energy. Energy is same, that is Ei, but you can find a number of states, Gi number of states are there. And this is basically called as degeneracy. Okay, what do you mean by degeneracy? If there are number of states corresponding to same energy, the particle has same energy, but they have different states, and this situation is called as degeneracy. Now to find the thermodynamic probability or statistical probability, consider a distribution of Ni number of indistinguishable particles with energy Ei occupied in Gi number of states. Okay, there are Ni number of particles. The energy of particles is Ei, that is ith state, and those particles are occupied in Gi number of states. Remember, Gi is the number of states available. Ni is the total number of particles. Energy of the particle is Ei. Each particle is Ei. And we know that in B statistics, there is no restriction on number of particles to occupy the given state. Any number of particles can be put in the given state. Now, according to this condition, let us consider an array consisting of Ni particles and Gi states. And I will represent the particles as dots and states are represented by lines as in this figure. Okay, so this is the first state. Line represent one state. First state consists of 3 particles. Second state consists of 2 particles. Third state 1 particle. Fourth state is having 4 particles. Fifth state is having no particles. So this is one array. So states are represented by lines. Dots are representing the particles. So you can rearrange them in any manner. This is one possibility. Whatever the figure showing is one possibility of distribution of total 15 symbols. Okay, so lines are representing the states, dots are representing the particles. So what are the total number of ways in which you can distribute these symbols, states and dots? So that can be given by this particular method. In the array, there are total Ni plus Gi number of objects. Okay, so lines and dots, if you combine them, totally there are Ni plus Gi number of objects and can be arranged in number of ways. Okay, different number of ways are there. Now suppose first state is fixed. Suppose the first state is fixed. That means this should start from the line only. The state should start here, lowest state. Other particles are. Okay, lowest state is that cannot be changed, that is fixed. Then according to permutation, the remaining symbols, that is Ni plus Gi minus 1. Why minus 1 is appearing here? Because the first state is fixed. That cannot be changed. Its position is fixed. The other symbols can change their positions. So what are the number of other positions, other symbols? That is Ni plus Gi minus 1 objects are there. And according to permutation, how many number of ways you can arrange them is Ni plus Gi minus 1 factorial. So much number of ways are there. That is in accordance with the permutation. You know that if there are Ni particles, you can arrange Ni particles in different ways. And the number of ways is Ni factorial. Okay, that's very simple. Since particles are indistinguishable, since particles are indistinguishable, the symbols, that is dots, are going to be indistinguishable. If you change first particle with the second particle, that is not giving you different state. It is same way because they are identical to one another. Okay, first particle may be put in the second particle place, but that is not giving you the different state. That's why you have to exclude these identical combinations. So you have to exclude Ni factorial permutations among Ni particles. So they are identical. Okay. Similarly, Gi minus 1 factorial permutations among Gi minus 1 states, they give identical arrangements. You have to exclude them. Okay. So that's why what you can get the final thermodynamic probability in which Ni particles can be arranged in Gi number of states. That is given by the omega I is equal to Ni plus Gi minus 1 factorial. That is total number of ways in which these symbols are arranged divided by exclusions of identical arrangements. So that is Ni factorial into Gi minus 1 factorial. So this ratio gives you total number of ways in which these states and particles are distributed. I have given you an example in the previous class, and also I have given you the appendix part in the notes. You can go through that. So there I have discussed this particular formula and validity of this formula for the known number of states and known number of particles. You believe me, this is the number of ways in which the particles can be arranged according with the BE statistics, Bose-Einstein distribution function. Only thing is here particles are identical. That's why you have to exclude the identical arrangements. Okay. Here this omega I is the thermodynamic probability of ith energy state and whose energy is EI. So this is the thermodynamic probability. Now we have to derive the expression for Bose-Einstein distribution function. What you can do? So if this is the expression for thermodynamic probability of ith state, you can find out what are the total number of ways in the entire system. Okay. If there are n number of states where I runs from 1, 2, 3, etc., first state, second state, third state, etc., then if there are total number of ways in distributing capital N number of particles in n number of energy states, small n number of energy states, then entire system will have the thermodynamic probability omega, which is equal to product of omega i's, where I runs from 1 to n, omega 1 into omega 2 into omega 3, like that it will draw. What is omega I? Omega I is the distribution of particles in ith state. There are such n number of state, I equal to 1, I equal to 2, like that. So finally, the total thermodynamic probability will be product of omega i's. What is omega I? It is a product of total ni plus gi minus 1 factorial by ni factorial into gi minus 1 factorial. So this product gives you the total thermodynamic probability of the system of n number of particles having n possible energy states, small n number of energy states. This is the thermodynamic probability. Okay. Now we have to apply this thermodynamic probability to find the entropy in accordance with Boltzmann's theorem. Okay. So Boltzmann's theorem says that S equal to K ln omega. Omega is known to us. You find out ln omega and you put that in the Boltzmann's theorem. Then you can derive the expression simply. Okay. So if Ni and Gi are very large, the number of particles are very large in number. That's why we can neglect the value, the number 1 here in the product. Okay. Since number of particles and number of states in the system are very large, they are very large compared to 1. That's why I can neglect the number 1 here. That's why the thermodynamic probability in B statistics for large values of Ni and Gi, the thermodynamic probability becomes omega is equal to product of Ni plus Gi factorial by Ni factorial into Gi factorial. Okay. So then you take natural logarithm on both sides. Okay. To determine the B statistic function, you take natural logarithm on both sides. So that will give you ln of omega, which is equal to ln of product of Ni plus Gi factorial by Ni factorial into Gi factorial. You know that ln of products is nothing but sum of ln of individual terms. So ln of m divided by n is given by ln of m plus ln of n, like that. So therefore this product becomes summation. Inside the summation you will get ln of Ni plus Gi factorial. Since it is m by n, you will get minus ln of Ni factorial minus ln of Gi factorial. This is converted into summation. If you apply the ln to the product, that will give you the sum of ln of individual terms. That is in accordance with the logarithmic identity. Now you apply Stirling approximation to find to simplify this particular expression. Okay. So you know that the Stirling approximation gives you ln of n factorial is nearly equal to n ln n minus n. So ln of n factorial is given by n ln n minus n. So substitute here, or you apply the Stirling approximation in this expression. That will give you ln of ni plus gi factorial is given by ni plus gi into ln of ni plus gi minus ni plus gi. It is n ln n minus n. Okay. Similarly, you apply here, that will give you minus ni ln ni plus ni. Plus into minus, sorry, minus into minus, it becomes plus. Okay. Minus n is there. Then the last term, it will give you minus gi ln gi plus gi. Okay. So this is the expression. Okay. Simplified further. So here this ni gets cancelled, minus ni plus ni, minus gi plus gi, that gets cancelled. You will left with only logarithmic terms, that is given by summation of ni plus gi into ln of ni plus gi minus ni ln ni minus gi ln gi. Okay. So this is the expression for ln omega. Then you have to apply this ln omega to the Boltzmann's theorem. Then according to Boltzmann's theorem, the entropy of the system is related to omega by the relation S equal to k ln omega, where k is called as Boltzmann constant. And we know that for the most probable distribution or for the equilibrium distribution, the entropy of the system must be maximum. If entropy is maximum, the derivative of the entropy must be equal to 0. That is well known to us. So if the function is maximum, then definitely first derivative of that function should be 0. Since k is constant, you can put dou s equal to 0. It means that k into dou of ln omega must be equal to 0. That means derivative of this ln omega with respect to ni must be equal to 0. So therefore, you will get dou of ln omega equal to 0. You substitute here, or you apply that condition here, you will get the derivative of that above equation, that is dou by dou ni of omega, ln omega. Ln omega is given by ni plus gi into ln of ni plus gi minus ni ln ni minus gi ln gi. That should be equal to 0. So what I have taken? I have taken dou by dou ni of ln of omega. Ln of omega equal to this summation. Okay. Now you differentiate this equation with respect to ni partially. It is a partial derivative differential equation. You have to take gi as a constant. Okay, number of states are constant, and you have to differentiate this with respect to ni. So first term, that will give you ln of ni plus gi. Okay, if you take the derivative of ln of ni plus gi, that will be 1 by ni plus gi. Okay, then derivative of this one, it is going to be 1 into ln of ni plus gi. Okay, you will get ln of ni plus gi plus 1, and the derivative of this ni ln ni, it will give you minus 1 minus ln of ni. Okay, and the last term, derivative of the last term will be 0. I have skipped one step here. So you left with the summation of ln of ni plus gi minus ln of ni into dni must be equal to 0. That is the expression for the dou by dou ni of ln omega. Okay, so this expression you will get. One step I have skipped. Basically, you will get one term plus 1. Corresponding to this, you will get one term minus 1. Plus 1 minus 1 gets cancelled. You left with this one. So derivative of ni ln ni, that is, you have to apply the product rule of differentiation. First term is ni, second term is ln ni. Okay, so you will get ni into derivative of ln ni is 1 by ni. That will give you 1. Ni by 1 ni, that is 1. Then second term is derivative of ni into ln ni. What is derivative of ni? It is 1. 1 into ln ni. You left with minus 1, then minus ln ni. Okay, that 1 gets cancelled with this term. Okay, so then you rearrange it. So this must be true if and only if each and every term in the summation is going to be 0. Now you use conservation laws equation and you add these two terms to this summation. What you can do, we consider this conservation loss dni equal to 0, summation of ei into dni equal to 0. Now you multiply these two equations by the Lagrangian undetermined multiplier, because we have to find the distribution function as a function of energy. But in this equation, there is no term energy. Because of that, we have to introduce the term energy from the conservation law. Multiply these two equations by Lagrange's undetermined multiplier, say minus alpha and minus beta respectively. So since this equation gives you the value 0, the multiplication of this equation by some non-zero number will not change the right hand side. That's why we can multiply the first equation by minus alpha, second equation by minus beta. Add these two equations to this summation. So it is nothing but adding the zeros. It will not change the identity. That's why the above equation becomes ln of ni plus gi minus ln of ni minus alpha minus beta ei into dni equal to 0. So where alpha and beta are Lagrange's undetermined multipliers, and they can be determined such that the term in the bracket vanishes for each value of I, or this equation is valid if all the terms in the summation are zeros. Okay, then individual term should be 0. So then what you can get? Individual term, each term should be 0. Therefore, ln of ni plus gi minus ln of ni minus alpha minus beta into ei must be equal to 0. So rearrange. So finally, we need the expression for a distribution function. What do you mean by distribution function? It is a ratio of ni to gi. That ratio you have to find. You have to find the ratio of ni to gi. So rearrange. You will get, if you combine these two, you will get ln of ni plus gi by ni. Okay, it is of the form ln of m minus ln of n. That's why you will get ln of ni plus gi by ni. It is of the form ln of m by n. Okay, minus alpha minus beta ei, that is equal to 0. Okay, so if you rearrange this, you will get, if you take this alpha minus beta ei to the other side, you will get plus alpha plus beta ei. If you convert this logarithmic equation into exponential equation, you will get ni plus gi by ni, that is equal to exponential to the power alpha plus beta into ei. What you can do, you can convert the logarithmic equation into the exponential equation. We know that ln of m is equal to x. If it is the form of the equation, then definitely the value of m is equal to e to the power x. Okay, so this equation you have got. Finally, what we need the ratio of ni to gi. So you will get a gi by ni. So you can write this as ni by ni, that is 1 plus gi by ni. So that will give you gi by ni is equal to e to the power alpha plus beta I ei minus 1. Okay, what do we need? We need the expression for ni by gi. Therefore, ni will be equal to gi by e to the power alpha plus beta ei minus 1. Or ni is nothing but gi into f of ei. And this f of ei is called as distribution function. If you compare these two equations, you will get the expression for distribution function f of ei as 1 by e to the power alpha plus beta ei minus 1. So this is called as Bose-Einstein distribution function, or BE distribution function. And here you can prove that the value of beta, in the above equation, the value of beta can be given by beta is equal to 1 by kT, where k is Boltzmann constant, T is the absolute temperature of the system, and the value of alpha can also be found as per the procedure we have done in the MB statistics. We have done that. You have found the value of alpha and you have expressed that value of alpha as a partition function. So here beta is given by 1 by kT, and you can apply here. So finally, the Bose-Einstein distribution function takes the form f of BE of as a function of E, that is equal to 1 by e to the power alpha plus e by kT minus 1. Okay, So these are all mathematical steps, one by one you can understand clearly. And finally, we have got the expression for Bose-Einstein distribution function as 1 divided by e to the power alpha plus e by kt minus 1. And this gives you the probability of distribution of particles in the energy state of energy E. Okay, so this is called as Bose-Einstein distribution function, or simply BE statistical distribution function. Okay, so finally I will conclude. The Bose-Einstein distribution function we have derived, and that is given by FBE of E, that is equal to 1 divided by e to the power alpha plus e by kt minus 1. This is Bose-Einstein distribution function. So this gives the condition or distribution of indistinguishable quantum particles. So the particles has to be identical in a given number of energy states in accordance with Bose-Einstein statistics. Okay, this is the expression which is giving you the probability of distribution of indistinguishable quantum particles. And finally, the particles which obey BE statistical distribution function are called as bosons. Okay, the particles which obey BE statistical distribution function are called as bosons. And also you have to remember that the BE statistics applies to the particles with integral spin particles only. Okay, it is applies to the whole integral spin particles such as photons, okay, gas molecules. So spinless particles and integral spin particles. So they obey this Bose-Einstein statistics, and those particles are called as bosons. Okay, so what are bosons? Bosons are the particles which obey BE statistical distribution function. So the BE statistics does not restrict the number of particles in the given state, or Pauli's exclusion principle is not applicable here. Okay, you can put any number of particles in the given state, and therefore the BE statistics applies to the particles such as photons, phonons, deuterons, mesons, and which have the whole integral spin, and these are called as bosons. So these particles are the examples for bosons, and they obey BE statistical distribution function. So this is all about the BE statistic distribution function, and application of Bose-Einstein distribution function we will consider in the next class.